This is a pretty short module, but we're just going to talk about programmable logic, and that leads into the FPGA, which we use today. All right. So this is all just about history of where we came from in terms of probably the second most popular type of technology that we use to implement digital systems with. So you might notice that when you go into lab, a lot of stuff is happening. Okay, you have this little board that's just a miracle. So you're writing VHDL, you're hitting a button, magic happens, and all of a sudden it appears on a chip. Okay, all the stuff that happens between when you hit compile and download to it showing up on the FPGA is just incredible. So that you can spend an entire graduate degree just trying to understand all the steps in that process. Okay, so we are not necessarily we're interested, but we're not necessarily covering the algorithms that take, what your design and actually synthesize and create all the gate level schematic that goes on the FPGA. But we do want to know how to model digital systems, so that's what we're doing with VHDL. And we also want to know more about the hardware, because if we know what the VHDL is going to synthesize onto, it helps us make better design decisions. And it also will help you when you become like an engineer and you're going to design a system and you say, well, I need a little thingamajig that does this. Should I choose a microcontroller or should I choose an FPGA or some other equivalent device? Okay, so we just want to look at kind of the history of programmable logic. All right. In the beginning, there was a sum of products. Okay, you have a sum of products form. Remember what this is? This is our little AND gates, which are product terms feeding into an OR gate. Okay, and so you have a logical sum of logical products, and here's what you got. You got yourself this sort of stuff, and that form can implement any combinational logic expression there is. Okay, so immediately upon the invention of the integrated circuit, okay, which was like the 60s, what they decided is that, okay, we are always implementing all of these combinational logic circuits. Any logic expression can be expressed in a sum of products form, and so why don't we stop spending so much time creating these custom integrated circuits with sum of products, and let's do something that is programmable or quasi-programmable, where we can actually take an approach kind of like the MROM, where we fabricate a bunch of stuff that we know is going to be a sum of products. It's just that we don't know what the final logic expression is. So if you don't know the final logic expression, but you do know that it's a sum of products, you can actually just go into a chip and throw down the AND gates, right? And you can go down and throw the OR gates too. All that's really left is programming up which inputs are tied to the AND gates and which AND gates are tied to the OR gate. Okay? So that gets us to kind of the historical aspect of the first programmable logic device, and it was called a Programmable Logic Array. Okay, and this was 1970s, and it was a company by the name of Texas Instruments. Has anyone ever heard of that? Okay, these guys were huge, right? They're still around, okay, but these guys were, when you look at the history of what happened, all of this stuff, like all of your parts that you used in 261, all the basic gates, Texas Instruments was the leader in that. They were the ones that fabricated all that, the first generation of logic families. They also were one of the first people to come up with this whole programmable logic array concept, and that launched everything until we get to today. Now, their company has changed a lot over the years. They kind of went into microcontrollers and DSPs, and then they kind of backed out of it, and now they're into a whole bunch of different areas. So historically, they're not necessarily, this isn't their bread and butter anymore, but this is where it all started. Okay, so this is a programmable logic array, and the architecture looks like this. They would go on to an integrated circuit, and they would start fabricating. And what they would do is they would fabricate AND gates. Okay? And if you think about a sum of products, you're going to have some inputs. Okay? So let's just say you had into this system 4 inputs. Okay? A, B, or let's do 3 inputs. A, B, and C. Okay? You know that in the worst case scenario, you would have a logic circuit that would have product terms which would include all of those inputs. Correct? Some of them might be inverted, some of them might not be included, but in the worst case, if you had 3 inputs, you know, the largest number of inputs on an AND gate would be 3. Okay? And so what they did is they said, okay, why don't we bring all the inputs and their inversions into each of the AND gates? And so what they did is they said, okay, I'm going to have an A, I'm going to have a B, and I'm going to have a C, and I'm going to bring them down, and I will also take these guys, and I will create an inverted copy of it and bring them down. Okay? And then what I'll do is say, okay, now I've got all these puppies and their inversions. And then what I'll do is I'll route all of them over and get them ready to be connected into the AND gates. Okay, so this is my equivalent of them being routed over. Okay? But we don't want to connect them yet. So what you do is you say, get them ready to go, and then have a little thing that will allow us to make the connections once we're ready to implement the final logic expression. Okay? And the final logic expression will come from the customer. Okay? So this right here is what we call an AND plane. Okay? So this is an AND plane. And it is essentially programmable. Because if you come along in here and you put these connections in, then the inputs or their inversions will be routed to the AND gate. Okay? Now, this puppy, the way they would do this is implement it all the way to the point where these connections were not made, and then they would wait for an order. All right? Now, the next part of this would be an OR gate. So you need the OR part of it. So what they would do is they'd come down here and they'd put an OR gate, okay? And the OR gate would have an output, single output. And then what they would do is they would bring all of these bubbies down here. So they'd bring them all down into the OR gate, okay? And then what they do is say, okay, instead of connecting those up, we'll have a programmable region here also. Well, guess what? You know what would be also cool is what if we could have another output, so let's do like an F1 and an F2, and we could kind of do the same thing where we do this sort of thing, and depending on a logic expression that comes in, if you didn't use all your resources, you could conceivably make one circuit that just used these AND gates, and then one circuit that used these AND gates. Okay? So this over here was called the OR plane. Okay? And this was the programmable logic array. This was the start of it all. And it was literally, they would fabricate it up except for these connections. They would get the order. You would like send them a file that says F is equal to A naught BC ORed with AB. And they would go in, they would add the connections, voila, put it in a piece of plastic and ship it to you. Okay? It was much cheaper and much faster to do it this way than it was to actually create a custom integrated circuit that had your logic expression on it. Okay? All right, so that was the beginning. How's that feel? You're like, could you draw that a little better? Voila! Check this out. Now, this is the exact same thing. Programmable Logic Array, PLA, and it makes a lot of sense. And this is what it looks like when you draw it without a pen. How's that feel? Okay, life is good. Life is good. So one of the ways that you would actually give them your schematic would be like this. So what they would do is they had like these sheets that you would download, like pieces of paper. Okay, this is 1970s. All right, and you would actually get this schematic, and just to reduce the number of lines going every which way, what they would do is they would just kind of treat these as like a bus right here. This puppy right here would be like a bus. So it's one line going in, but it represents a whole bunch of signals going in. And what you would do is whatever you wanted to connect, you would just draw an X on it. Okay? And so if you looked at how they would do this, you'd come along here and you'd go, okay, I want A to be routed into this AND gate, so you would come along and you'd actually put an X on this. And this is, I'm talking like with a pen. Okay, you would do this. And then you'd say, okay, I want to do this one. I want the B naught to be routed in. And this expression right here, that would communicate to Texas Instruments that you were doing an A B naught product term. Okay? And you would literally mail this stuff. Okay? This was 1970s. They didn't have, I think they had email maybe, but it was pretty new. Okay? So you'd put it in an envelope, lick it. Has anybody ever done this? You probably have never heard of this. There's a thing called the United States Postal Service. Okay, have you ever heard of these things? Okay. Before electronic mail. Then what you would do is say, okay, I want to bring this puppy, this product term in, this product term in, this product term in, and this is how you would communicate it. Now, you will never do this again but you will never probably see this again, but it's just historically, it was kind of interesting to do. Okay, so what do you think the limitations of that was? Well, it turns out that if you look at this, you've put a whole lot of stuff down in order to implement everything under the sun. Primarily, or namely, one of the things that sucked about this is that you had all these interconnections for these OR gates, and what happens is that it started adding a lot of delay. So you had a lot of OR gates that were consuming power. You had a lot of metal running every which way. You had to have the capability to connect these during fabrication. So they said, why don't we get rid of that, and let's go on to a new thing, which would look like this. So they created what you call a fixed OR plane. Okay? And what that means is that the OR gates were already wired up for you. Okay? But you still could program the AND gates. Okay? That was good. So another company started coming up with this architecture, and they said, we love what Texas Instruments is doing. We're going to make PLA2 or something like that. Well, Texas Instruments got all ticked off, and they said, no, 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 PLA is our name, and they copyrighted it. Okay, so it was like a trade name, even though PLA is like, it rolls off the tongue, okay, and it's Programmable Logic Array. It makes so much sense. Nobody else could use it besides Texas Instruments. So this company came along called Monolithic Memories, and that ultimately became, any idea? Not Intel, not Micron, AMD. Okay, so this was kind of the start of it. So they came up with the PAL. Okay, PAL rolls off the tongue, but when you say it, it's stupid. Programmable Array Logic. Okay, so it seems backwards. So the reason it seems backwards is it was a copyright thing. Okay, so they also said, boy, that whole thing about having it fabricated at the shop and then you tell me what it is and you guys finish the fabrication and then send me the chip. I would like to try to copy what they're doing with like double EEPROMs where you blow fuses, okay, or PROMs or double EEPROMs. Well, PROMs. So what they did is they put fuses in here. So this architecture right here, this is what exploded, okay? So Texas Instruments had the great idea, but they weren't the first ones to get the fuses on there or do the fixed OR plane. So this chip right here became the one where you could buy like 1,000 of these things, and you would have a programmer at your company, and you would actually just put it in there, you would type in your logic expression, hit go, it would blow all the fuses, and you would have it. Okay? So this was what really started taking off. So that's why we see PAL in a lot of the things that came later. Okay? And this was all also in the 1970s. Okay, okay. Now you're like, man, this is sweet. So you have a programmable array logic. Okay, so you have a PAL, and this creates combinational logic. Okay, what immediately do you want to do? Everybody's building finite state machines. Okay, so you would have a D flip-flop component, just like you guys used in 261, and then you would have these PALs, and the PALs were awesome because they would give you these logic expressions. So you could build a finite state machine and use PALs for your next state logic, and you could use PALs for your output logic, but you were still putting D flip-flops down and building like these pretty big circuits. And that's how like the first digital systems were made. But what do you think would make this even more useful if you had one chip? It would be to include the D flip-flop on here. Now, you don't want to hard code a D flip-flop so that it's always a D flip-flop. You'd like to be able to use it as a D flip-flop. You'd also like to be able to use it as a combinational logic circuit, or you'd like the combinational logic to drive into the D input of the D flip-flop. So, how could you create an architecture like that? Well, what they came up with was an idea that looked like this. Consider that you had a D flip-flop right here, okay? And it had the output of the PAL routed into the D, okay? But if you wanted just the PAL output, what you could do is you could say, okay, sometimes I want to have the output of the D flip-flop, okay? But other times I'd like to have the output of the PAL, so I'll use a multiplexer. And depending on an output select line, so this is going to be output select, you could choose whether you got the output of the PAL, which is combinational logic, or the output of the D flip-flop. Now think of the magic of this architecture. The output of the D flip-flop, if you wanted to wire this up and have it just be a D flip-flop, What would you do with the PAL? The PAL's a frickin' combinational logic circuit. What would you do with your PAL if you didn't want to have any logic in there? It's a programmable array of logic, so what could you do? Program it to be a wire, exactly. So what they would do is you would just put a logic expression that's like F is equal to the input. And you would implement that, and then you would have yourself a little bit of D flip-flop action. If you wanted a finite state machine where you were going to have this feed into the D flip-flop, and this would be like your next state logic, and this would be your state memory, all you would do is then program up over here whatever logic you wanted, and it's already wired directly into the D. So you got all three configurations that are sweet. Okay? All right. Now, what they said is, well, we want to start interfacing these things back. So we'd like to have this thing potentially use the output of itself as an input. Okay? Where the hell would you ever see that? Using the output of itself as a potential input into the combinational logic. Finite state machine. Let's go below the line. And if you think about a finite state machine, you've got your state memory right here, and you've got your next state logic right here. So you got next state logic. Okay? Well, this drives into the current, so this is the current state. And then on the output, that's not even close. This is the current state. This is next state. And what do you always do? You always take the current state and you always route it back into here. Okay? So they had this need to take this puppy right here and drive it back into the actual puppy itself. Okay? So you'd use this puppy and bring it back. And then they said, okay, if you're going to bring your dude back, okay, that's only one bit of the state code, right, of the current state code. You got to be able to bring other ones back also. So what they ended up doing is they said, okay, let's put a output transceiver. Remember the transceiver that we've looked at where you have basically you have a buffer and that's driving it, but it has to be tri-state and all this sort of stuff, and then you have an input and all that sort of stuff. So what they did is they drew it like this. They have an I/O pin or groups of pins. And then what they would do is they'd come over here and they would have a tri-state buffer which would allow it to either drive to the outside world, or if you wanted to bring this puppy in, you could actually bring it in and you could wire this now as an input into the programmable logic. Okay? And what you could do is you come over here and it's like, oh God, now we got two things coming back. What do you do when you have two things coming back and you want to handle which one you choose? They would actually come in and do another multiplexer. Okay? And then they're like, well, if we got a multiplexer, let's bring this guy back too, just in case we want to create something really cool. So they started adding all this functionality. Okay? But you can see kind of the motivation for it. This had a specific name of all this stuff right here. They actually called this thing a output output logic macro cell. Okay? So it was kind of this really cool thingamajig. And it actually had an acronym, OLMC, but it doesn't spell anything, so no one ever uses it. Okay? That's word to the wise. If you're going to have an acronym, it's got to spell something out or else nobody will adopt it. Okay? You cool? That's for free. That advice is for free. Nothing to do with the course. Okay. You're like, Brock, can you draw that better? Bam! So I come along and I look at this and you go, you got to have a name for this thing. And so they called it the generic array logic, or the GAL. Okay, so here comes the GAL. This is awesome. Okay? And this was a pretty big contribution here because it provided almost everything you needed in order to implement some serious digital systems. Okay? And that was the GAL. All right, life is good. If you're going to have a GAL, what else do you need? A HAL, obviously. So just historically, if you think about that, a HAL existed also. And what the difference was is that this one was kind of all programmable in terms of like blowing it with fuses and everything. A HAL came along, and what a HAL was is that it was called hard array logic. And then this was basically one that it had the connections actually implemented during fabrication. So some people, you know, they said we need programmability or flexibility, programmable flexibility or flexible programming, flexible programmability, and they said fuses. Fuses are awesome. One of the things that happens though is when you put something in there like a fuse so that you can blow it with a programmer, you have to have a bunch of circuitry in there to support that. And any additional circuitry causes the system to be slower, okay, because it's got more interconnect to go through, more gates to go through. So some people said, I'm loving this thing and I can design big with this, but why don't we get rid of the fuses and just let me go back to the original do it during fabrication. So that's what the HAL was, okay, so that was HAL. All right. Life is so good that it had to just what? Get better, okay? It had to get better. Around 1983, okay, people are blowing fuses, right? People are doing HALs. And around that time, guess what else happened? The double EEPROM memory that we talked about was also maturing to the point. So this company, somebody created a company and said, what if we took the connections, those interconnections that people are, those guys over there, they're doing fuses, monolithic memories. They're going out of business, right? They became AMD, so they didn't go out of business, okay? TI, they're like, TI is old school. They're still around too, okay? So somebody in Silicon Valley said, let's create something where the interconnections could be controlled by a piece of memory since these other people already created a double EEPROM. So they integrated a programmable device, okay, so like a PAL, but they did the interconnections not as fuses or something you fabricate, but it was like a switch that was controlled by bits stored in a double EEPROM. And they put the whole thing on a chip, okay? So that gave you the ability to have something where you are going to program the logic, and if it's wrong, you know what you can do with the double EEPROM? You could then program the memory and change the interconnections. So it was the first time that you actually had a chip that you didn't have to throw away if you got it wrong. Now, remember what the first double EEPROM or EEPROM, okay? They first did it with an EEPROM. So the first programmable thing that you could reprogram over and over and over actually had one of those windows on it where you would shine UV light on. Okay, so if you go look at what this company's first product was, it was that. Well, that went away right away because the double EEPROM came out and they were able to do it with the double EEPROM. So now you have a logic circuit that you can program on the fly over and over. That was a cool idea. When things start going good and you have a little something, you put a whole bunch of somethings together and make life even better. So what people started doing was they started creating what they call complex programmable logic devices. Okay? So now what they would do is they'd say, we got these PALs, let's just cram them all together and get more and more logic. So the complex PLD was one where they would take a bunch of PALs and they would put in this programmable routing kind of switchboard so you could route things all over the place. And this is where you started saying, okay, my chip doesn't have like 5 logic expressions, mine has like 5,000 logic expressions. And you could start doing some huge stuff. The I/O was the macro cell. Okay, so they still had these macro cells in there, which were super important because you were trying to build complex digital systems. But this is the CPLD. Now you will hear people say CPLD. Okay? And what it represents is just a programmable logic device. Okay? Programmable logic device. There's really no other way to describe it other than PLD. But what you think about is that the history of it is bringing all this stuff together and getting to the point where you had an architecture built on basically arrays of PALs.